Okay, so let's get started with section 3.4, and we're going to continue with the log discussion. And before we get started, what we're going to do is, if I've got a bigger log function that I need to deal with, if I'm taking the log to the base b of two numbers, let's say if I'm multiplying, how do I handle this type of thing? Okay. When I'm doing it, I want you to consider that if I've got some number, right, that I wanted to do this, any number I can represent as a power of that base. Okay, right? That is the log function. So for some number, this would be x. That would be a. Okay. For some number, let's call this something else. Let's call this like a y. Okay. So this, I want to represent b. How would that be? That would be some number y. This would look exactly like b to the y. That would be this. Okay. This number is b. This number is a. So these two really I can represent as log b to the x times b to the y. Here's my a. That's just b to the x. My b, little b to the y, the base. And now I want you to think about this. These are the same numbers now. I've just got two exponents. And what do I do when I multiply two numbers? Let's go x to the m times x to the n. We just add exponents. Okay. So this, here's the exponents. So it looks like the log of this thing, log b to the x plus y, and this was the exponents when I'm doing this. Remember, that's one of our fundamental properties, that a log b to the x is just the x. This is just the sum of those exponents. Okay, and that is the log b of a. That's this piece. I got another pen here. This x was the very same thing as log b of a. This was log b of b. Okay, so it turns out that we can kind of do this and evaluate what this is just by representing these as logs, products of these things, and then see how they expand out. Okay, but keep in mind, logs are just the exponents. That's what exponents are. Okay, and I want to go through and look at those for each one of special cases: products, quotient, and powers. Okay, and what this is going to be enable us to do is break apart complex expressions and solve when the variable is in the exponent. But I may have something like 20 e to the x, and I want to know when this is 2000. And what I want to do is get this thing down. That's the basic log. The reason why we do logs is because we've got variables in the exponents. I'll be able to break this apart, solve for x, and say ... x is equal to something, and there will probably be logs in it, but I can do those on my calculator. Okay, that's what I want to do. I want to take a variable that's in the exponent and be able to solve for that. And these rules will help us get there. Yeah. So what are the basic properties? So here is the product. This one I kind of worked through. anytime I have the log, I need to take the log, or if I take the log, even though I may not need to, this was, do I need this number or I just need to break these things apart? This is the log of this one plus the log of that one. Same base, okay? All I have to do, multiplication goes to addition. Historically, if I needed to do some big multiplications, complex numbers, or big numbers, I would just go to the log table and I would turn multiplication into addition, and then to find out what the number, then I would go back to B to this and then find out what that actual was, okay? But here's the property. Multiplications go to additions. Okay, the quotients, remember what we do? These are exponents. And what do we do if I divide a number with exponents? The same number, I'm representing two numbers, and then I'm doing the division. Then this is just the top, the log of the top. I subtract exponents, I subtract the logs. Okay. And then finally, this, I get to move out front. So this is again exponents. I'm doing this multiplication p times. This would be x times x times x dot 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 x. This is done p times, that's what x to the p is. Well, I've got p multiplications. This is what we do when we do multiplications. We do additions. So it is the log of bx. I'm adding up p times or p times the log p of x. That allows me, this is like the very best of these things, is that I take an exponent and now I get it down. Okay, so no matter what I've got, I can get rid of, so if I have e to the x, now I can take a log and get this x, that exponent down here. This is just whatever that original number was. Okay, so for here. So if I were doing log, let me show you this one. So if the one that's the most important, if I needed to solve for x, that variable when I had this, and this was say, it would be the best. I'm going to do with the 10 first. Whatever this is, no matter the base, this comes out front, and it turns out to be x times the log 10 of e, okay? Now, if I'm smart when I'm doing this thing, I'll use the same base, okay? Doesn't matter, it'll come out to be the very same thing for x when I'm solving. But if I do this, this comes out. And now remember that ln of EE, this is the ln is the base E. That is exactly what that is. This thing is just 1, so this is just x. If you take the same base of whatever number you got, then it just works out to be that, and all of this stuff kind of collapses. Okay. So let's look at some different, some other stuff as we go. So use the product property of logarithms to write the logarithm as a sum, then simplify if possible, okay? I'll show you what that means. So I've got log. If I do log nothing 2xy, and I have to remember, if I just see this log by itself, understood to be 10. That's the common log. It's so common that we're doing base 10s all the time that we don't even write the base and we just understand it, okay? But I want to do this. This is all multiplications, so the logarithm, when I do logarithms, I turn multiplication into addition. So it's log of 2 plus the log of x, common log, base 10, plus log of y. Okay, so all of my multiplications go to addition with logarithms. There's no simplification in this case. No bases, there's no powers that I need to bring out, nothing of that. So that is my answer. That's simplified as much as I can get it. Okay, I want to contrast this. This is what I was kind of doing a little while ago. Log 2xy. This is base 2 plus log 2x plus log 2y. Multiplication goes to addition, but here's the simplification part. I can't do anything here, I can't do anything here, but now I've got this, I've got a base to base. I want to represent b as a 2, as a power of 2. What's the power? That's just 1. That's what the log is the power. This is just 1. Plus log 2x plus log 2y. And that is simplified as much as we can get it. We've done some preliminary. Okay. Let's do a couple more. 3a plus b. Now remember, this is multiplication between this and this. This is 3a plus b is 3 times a plus b. Okay, so that piece of it is multiplication, and I can break this apart to this plus the ln of this. Okay. This, you would like to go, oh, well, that's ln of a plus the ln of b, but it's not. You can't break this thing apart. The ln of a plus the ln of b is really the ln of a times b. So this piece of it is simplified. You stop at that point. You can't do anything. There's nothing you can do with an a plus b. There's nothing you can do with an a plus b. Okay? So that's fully simplified. So let's continue on. Some more examples. Write the logarithm as a sum and simplify as possible. So if you guys go and do your lab, Alex, they're going to say simplify as possible. And let's see if we can do some other simplifying. Okay. So here, log 4, 16 times a. Okay. 16 times a. Logarithms, multiplication goes to addition. So I go log 4, 16 plus log 4, same basis, a. And then once I get it kind of expanded, I want to go back and see if I can simplify. Is this any power of this? And it turns out this is 4 squared. 4 times 4 is 16. So I'm going to write this as 4 squared just for a second. And this is that exponent down, any of the exponents. I want you to kind of get used to saying, well, this goes down. Log 4, 4. Now this piece is just 1. So 2 times 1, here's 2 plus log 4 of a. Okay, so that's what this is. I want to represent 16 as a power of 4. What's the power? That's just the 2. Okay, and I did that just kind of working backwards. So any ways that you kind of want to work this through. Okay, that's what that is. Log 12 times CD. That's what 12 CD means. 12 times C times D. And that's just all multiplications. Log 12 plus log C plus log D. This is okay as long as, you're not getting too that you don't forget that that's what that is, okay? That I'm taking the log of this number. You know, sometimes I'll kind of go through and just write it real quick as this, but I know what I'm doing. But be careful that this needs to have parentheses around it. So what about when I'm doing quotients? I'm doing the very same process here, but now instead of when I'm doing quotients are division, I'm doing subtractions every time I see this. And sometimes I have a mixture, and I just have to have a just be careful with what I'm doing. Make sure I block everything with parentheses. So here's 0 over 49. I want to do log 7. I'm going to kind of emphasize this, the top minus the log of the 7, the bottom, okay? So I'm going to do whatever the top is minus the bottom, and then I'm going to break apart, if I can, any of this stuff. So this stuff I'm not going to be able to do, but I want to go ahead and get you used to that concept. It's the top, the log of the top, minus the log of the bottom. And do I have any multiplications in here? Multiplications or powers over there. But I got to subtract out everything that I do from the bottom, okay? So this is easy. This is just log 7. What is the top? That's z. Nothing I can do here. There's no relationship between 7 and z. I got to wait around for that number. And this is just the 49. But here, is there any relationship between 7 and 49? 7 times 7, 7 squared. Z, sorry, that's a z, minus log 7, 7 squared, whatever power goes down, and then this is just 1. Log of z base 7 minus 2, because all of this is just 1. And that's the simplification part of it. Okay, so that's what this is. Doing the quotient rule, log of the top, when I'm doing division, the log of the top minus the log of the bottom. Go through, and then if there's any way we can break that apart. Okay. So log 7a over 14. Is there anything I can do? So I've got the top minus the bottom. This is the first thing I want to do. So I don't want to start breaking apart the tops into sums. And here I want to go, this is equal to the log of the top minus the log of the bottom, same base, and then I want to fill this out. Log 2, 9 minus log 7, 14. I want to do this because this may be expanded if I do multiplications or something, okay? So this is A, there's nothing I can do, so I keep this as log, this should have been 7. Log 7 of A. So there's nothing I can do here, but this, is there anything with 7 in here to simplify? And 7 is what? 2 times 7. Okay, so this, now this is multiplication, so multiplication goes to sums, but I'm subtracting all of this because it was from the bottom. Log 7 of 2 plus log 7 of 7. This is 1. Same base in the number. Log 7a minus, now I'm going to drop this and realize that this is 1 plus 1. So minus log 7.2 minus 1. So that's fully simplified, as much as what we get. Okay, this, I'm not worried about this so much. If I just got to this point, I would kind of stop. But if you're doing standard, here's Alex stuff, you may want to try to work this thing all the way out to get the right number. That's why it would be fussy. Okay, it would want you to completely simplify if possible. Okay, so next example, what if I've got this? I want to evaluate the log of 100 divided by x plus y. Okay, and again, why am I doing this? If I have some exponent here that I need to solve for, right? So I have some complex formula, and then I have some power of this thing, and I need to find out what power makes it a particular number. Logs enable me to break apart complex things. Now, this wouldn't do a whole lot of good because of this addition. You'll see this in a minute, but we could do it for maybe this power, or if this was a power of all of this. So the log of the top minus the log of the bottom, so the log of the top minus the log of the bottom. And here is where I can't really break this apart. So if the power was in here, the way if this multiplication, I can do it, but with this, I have to stop. There's no simplification I can do with addition. Okay, but this, understood that the log is 10. Is there any relationship here? Yep. This is 10 squared. 2 goes out front, and then the log 10 of 10 is just 1. So this is 2 minus the log of x plus y. So here's the difference, kind of the same thing. There's not going to be much simplifying once you do, but here, this is just the log of the top. The ln, so this is the natural log minus the ln of 12. This, I understand, that's the same base, so this is just 1 minus the natural log of 12. Again, historically, books only had it for like the small numbers, actually between 0 to 10. Everything had to be written in scientific notation, and then you would go to the log book to find out what it was, and you could work the answer. Okay. So let's do this power property. This is the most important one of all. They're all important, but this is where it really gets useful, is because of the power property. We can bring exponents down, and when that exponent happens to be a variable, that gets us the very same thing. It turns solving an exponential equation into just a simple linear equation, but then I'm going to use the log values. Okay. So simplify this. Well, this is just x times x times x times x 5 times, or 5 times. So I would add up all of those ln's, or just do multiplication. 5 times the ln of x. ln of e to the 5th. 5 times ln of e. ln of e is just 1. That's the same base. So this is just 5. And here, let me represent, so this, anytime I have a radical, anytime I have this is all the log of that. I want to represent this with rational exponents. Okay. So here, this I want to switch out to here's x. squared, that's the very same as the top. Now this is the denominator. Now this is a power that can go out front, whatever that is, log of x. Okay. This was very useful when I wanted to do, if I needed to do what is the cubed root of 76 squared. Okay. That would be 2/3 the log of 76. Again, scientific notation, represent this, go through, find this number, and then all I'd have to do is this now turns in just a multiplication and a division. Exponential and a root is just a multiplication, and then I would do the inverse to find out what the number is, right? Then I could do the inverse, whatever that, take that to a power. I would go to a table of anti-logs. That was what, and then that would give me the inverse log, which would give me the exponential. And that's how I did exponentiation of either irrational numbers, decimal numbers, those type of things. Okay. Okay, so this is the same thing. Nothing new here, nothing new here. This is 4 times the ln of x. 4/5 times the log 5 of x. Okay, so once we get through, here's the basics. We're going to start working on mixing these things together to fully expand. Okay, so we're going to have to apply more than one simple, it's not just multiplication, not just division, top minus the bottom. We've got a mixture of all of that stuff in there, okay? So here we want to do, I want to take the log to the base 3 of the expression 5z over w, break this thing apart so that I can evaluate each one. So my first step, if I've got a complex, I want to do the top, and if I've got a bottom, minus the bottom, okay? And I put this in parentheses because whatever this expands to, I want to have to subtract off everything, from there. So this looks like 5z now, minus log 3. There's only one thing, so I'm just going to write this as the w, okay? But I want to continue. And ask myself again, do I have any powers, multiplications, divisions here? This I do. So this multiplication goes to addition. Like that. And this is understood plus, so I can just remove this. Log of 5 base 3, the log of z base 3, minus the log of w base 3. Okay. Here's another one with multiplication in both the top and the bottom. Log of the top minus the log of the bottom. Now this negative this goes to addition. But this, I need to be careful and subtract off everything. So this is minus log 7, 5 plus log 7 of d. Close braces. So this is finally log 7a. I can't do anything here. Log 7c, I can't do anything there. Here, I subtract off each piece of it. And that's D. Like that. Okay. Top minus the bottom, get that out of the way. And then everything in the bottom should be negatives as you finish. As you check over this, all the top should be positive multiplications. Everything in the bottom should be a negative corresponding to that. Later on, we're going to have to bring these things back together. Okay. So let me do a couple more of these that are new. I want to do this. So this is multiplication here, ln x squared plus the natural log of y. Multiplications go to addition, and then any powers need to go out front. So this is 2 ln of x plus the natural log y. ln or natural log, I just always say ln. That's kind of what people do for the shortened version. Just ln means the natural log. Here again, we see the radical. We need to represent that radical as a rational exponent before we do any logarithmic simplification. So the ln cubed root of x squared over w plus z. Okay, the top minus the bottom. This I have to stop. There's nothing I can do with addition. Okay, but here I want to represent this as x squared, but I'm doing the cubed root. Okay, so I need that piece. And this is now exponents that go out front. 2/3 the natural log of x minus the natural log of w plus z. And not until we have these numbers, this I could add and then take the natural log. This you got to tell me what x is before I can do. So I have to leave these alone until I know what x, w plus z is. 3, 4, and 7, right? So all of these, top minus the bottom, and then break these apart. Let me do this one because it's kind of got a mixture of everything that we need to deal with. Here's log 8, log base 8 is how we do that. 64 x squared y, 3z w cubed. Okay, simplify. Okay. So the top minus the bottom is my first step. Log base 8, 64x squared y minus log base 8, 3zw cubed. And I've got to break this apart, so I'm going to go ahead and add a little curly brace here because this is going to be addition by doing this. But once I do that, that's all subtraction from the bottom, okay? Multiplication, let me take care of that. And then my curly brace expansion here, this is subtracting all of this stuff. Log 8 of 3. Plus log 8 of z plus log base 8 of w cubed, okay? So this piece, if it was up top, multiplication goes to addition, but that's going to switch all of these signs to turn everything into subtraction. Because we're dividing by that, we're dividing by that, we're dividing by that, okay? So now I want to go through and look at powers. Here's a x squared. and I want to simplify those. So log 8, 64, plus 2 log 8x, plus log 8y, minus log 8,3, minus log 8z, minus log 8. Now this is 3 times this, so I'm going to go here. This is a w cubed, so minus 3w. All my exponents need to be down in front. And then if I can do any simplification here, 8 squared is 64, so this is really 2. 2 plus 2 log 8x plus log 8y minus log 8,3 minus log 8z minus 3 log 8w. I know that's unwieldy, but that's how we need to go through and break those things apart. Okay. Okay, so the next step, we'll kind of work backwards from here, is to be able to take an expression like this and recombine them. Sometimes we need to go one way, sometimes we need to go another way. Okay, so here we're going from this, working backwards and seeing if we can put these things back apart, back together again. Okay, and later on, we're going to have to solve for a particular value. So this is just the practice. Simplification, break them apart, bring them back together. Later on, we're going to have to be able to do stuff like, when is this equal to 5? Solve for x. So I've got to be able to do these different simplification expansions, bringing them back together to work them in. We'll work on this later, okay? But again, right now we're just learning how to break them apart, bring them back together again as needed. Just an expression, not equal to anything. Bring them back in, okay? Write the logarithmic expression as a single log with a coefficient of 1. I don't want any powers out here, okay? So negatives, if I've got negatives, that's going to go to division. So all my positives are multiplications, and then negatives are division. So this looks just like that. And if I broke it apart, the log of the top minus the log of the bottom, that's where I would end up, okay? Log 2z plus 4 log 2y. The order that I kind of followed through, breaking them apart, multiplication, division through the subtraction, and then I did the powers. That's kind of what I want to do here. Before I bring these back together, I got to take care of the powers and bring them back here. So my first step looks like that. And then I've got addition. That's just the multiplication process. Like that. Any questions? You guys got this? We're going to work on this in class. We'll go back through these things through the homework and stuff. Tomorrow, we'll go work on some of those together. Okay? No questions? Tamika, I'm going to put this video up. It'll be as quick as I can late this afternoon, by late this afternoon. I know I was a little late yesterday, but it took a couple of things to get them all up there.
No problem. Thank you so much.
Okay, guys, let me grab your attendance. Let me get this. I've got it. So I will see you guys tomorrow. Have a good day.